Alright, so in this video I'm going to take a look at the turning point section of paper 3. This is from the second set of specimen papers. So let's get started with the equipment used to determine the specific charge of an electron. So this is our setup. We've got our location for the circular motion to happen, and we've got our electric field to accelerate it. So we've got thermionic emission to get our electrons, and then they're accelerated using an electric field. And then we've got helium gas at very low pressure, and we've got the gas emitting light to show where the electron goes. And we've got a circular path because we're using a magnetic field, and we know that magnetic force is always perpendicular to velocity, so that makes a circular path. Explain how light is emitted as electrons travel through the gas. So this is all about excitation. So the electrons are going to collide with orbital electrons in the helium atoms, and they're going to excite those orbital electrons. It's unstable to be excited, so they're going to de-excite, move to a lower energy level, and emit a photon. Alright, and that's what I've got written here. Essentially, these are the stages that are going to earn you the 3 marks for this question. Okay, so that finishes part 1. Let's move on to part 2. So we've got in one experiment, potential difference between the 2 plates of the accelerating electric field at 2.5 kilovolts show that the speed of the electrons is about 3 times 10 to the 7. So what we're going to do is equate the potential energy change in the electric field to kinetic energy. So the potential energy change in an electric field is QV, and it's an electron, so it's actually going to be EV, and that's going to be equal to half mv squared. And we want the velocity, so we're going to rearrange to make v the subject. So that's going to be 2eV, because we take the half to the other side, divided by the mass of the electron. So let's grab the old calculators and we can put those values in. So we've got 2 times 1.6 times 10 to the minus 19 times 2,500 divided by 9.11 times 10 to the minus 31. Square root that answer, and it comes out as 2.96 yada 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 times 10 to the 7, which is approximately 3 times 10 to the 7 to 2 significant figures there. So we've shown that it is indeed what we were trying to prove it was. Okay, so that finishes part 2. Let's move on to part 3. Okay, so we've got the flux density and we've got the diameter of the path taken, so we want the value of specific charge. So if it's moving in a circular path, what we can do is equate the equation for centripetal force with the magnetic force, because that is the force causing the circular motion. So that's what we can do. So we can cancel out the v's and essentially get an expression for the charge divided by the mass. So what we're going to do is we're going to take b over to the other side, is v over b r. So we've just calculated what the velocity was. It was at 2.96 blah 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 times 10 to the 7. We've got the field strength, 3.1 times 10 to the minus 3. And we've got the diameter, which we need to divide by 2 because we want the radius. So when we do that, so let's divide by 3.1 times 10 to the minus 3, divide by 0.114 times by 2, and we get 1.67 blah 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 times 10 to the 11, which is going to be 1.7 times 10 to the 11 coulombs per kilogram. And if you look in your formula sheet, you should see that's pretty close to the actual value, so it's a useful way of checking you've got the correct answer here. Okay, so that's the specific charge. In practice, the path of the electron is not a perfect circle. Discuss how the presence of the gas affects the path of electrons. So when electrons collide with the gas atoms, their velocity is going to decrease. And if the velocity decreases, that's going to affect the radius of the path. So let's get that equation back up. So we know that if we rearrange the equation, the velocity is going to be calculated by doing B times R times the specific charge. So the specific charge of an electron is a constant, as is the magnetic field strength. So we can see that if the velocity decreases during collisions, that's going to make the radius of the path decrease. And so what's going to happen is as they collide with gas particles, you're going to get them spiraling inwards in their path. So let's put that into words now. Okay, so that's what we've got here, and then I've separated out into the three what I reckon would be the marking points. So this is the equation we're using. This is what happens to the velocity. This is therefore what happens to the radius. So then what does that look like? It looks like it's spiraling inward. So those are the stages I would go through there. So that finishes question 1. Let's move on to question 2. Okay, so we've got a graph where the solid line represents how the intensity of radiation from a black body varies with wavelength at a particular temperature. So we can see that this particular wavelength is given off strongly, and then these ones less so much. And the dotted line shows the variation is predicted by classical physics. So you can see that in the dotted line there. So explain why the difference between the predicted and experimental values is called the ultraviolet catastrophe. So you can see that the classic physics prediction is that essentially we should keep on going. So when we at these shorter wavelengths, we should find a large amount of them. However, we can see that at the shorter wavelengths, which correspond to the ultraviolet range of the spectrum, they are missing, and that's why it's known as the ultraviolet catastrophe, because they couldn't explain why these parts were missing. So let's get that down. Okay, so that's the ultraviolet catastrophe. So then it wants us to describe the difference between the classical physics view and the quantum theory proposal made by Max Planck that enabled the distribution of the shape of the intensity wavelength graph to be correctly predicted. So Max Planck is most famous for his work on quantum physics. So Max Planck proposed the idea that energy is given off in discrete quanta of energy. So that was Planck's prediction. Classical physics at the time believed that radiation was emitted continuously. So essentially it was in the form of a wave continuously emitting energy. So those are the two differences. So let's put that down. All right, so let's get that down. So this is essentially investigating the observations of the photoelectric effect in many ways. So you'll remember from year 12, with the photoelectric effect, there were different predictions for wave theory and particle theory, and that's essentially what this question is expressing. Okay, so let's move on to part 3. So part 3, discuss the evidence that the photoelectric effect provides us in support of quantum theory. So the evidence, there's two clear pieces of evidence. One is the threshold frequency, and the other is instantaneous emission. So let's first explain how this works. So for any material, there's a minimum energy required to emit an electron. That doesn't matter whether we're dealing with wave theory or particle theory. There's a minimum energy called a work function. And because classical physics predicts energy is supplied continuously, any wavelength should be able to cause an emission, because it just takes a while for that amount of energy to build up. But in terms of particle theory, because the energy only arrives in discrete quanta, if the photon doesn't have enough energy, there can be no emission, and that's where the idea of a threshold frequency value comes from. So let's put that down. Okay, so the first point is that there's a minimum energy required to emit an electron from a material called a work function. So now let's explain what wave theory or classical theory predicted. Okay, so that's what we've got next. So classical theory predicts that any wavelength can cause an emission, whereas particle theory predicts, or Max Planck's theory predicts, that only radiation in which the photons have energy greater than the work function can cause an emission. And in terms of the evidence that was found, it was found by experimentation that electrons are only emitted when the frequency of radiation is above a fixed value, which is evidence for particle theory. So that's really the final nail in the coffin for the classical theory. The fact it predicted something that didn't happen is when a theory gets completely discredited in science, because that's how we put them to the test. Okay, so that finishes this question 2. Let's move on to question 3. Okay, so generally speaking, what we're looking for. So we're looking at a diagram to start with and explanations of how we're going to measure the speed and kinetic energy. So what we're going to have is a plate over here that we're going to send the electrons towards, and we're going to have a particle accelerator over here that is essentially sending electrons this way in bursts. And between the two, what we need to do is connect an oscilloscope. Because that's what's going to allow us to see when the electrons leave and when they arrive, because we're going to get pulses. So in terms of how this is actually going to work, let's start explaining that now. So first off, what we're going to do is we're going to use our particle accelerator over here to send pulses of electrons, and in the actual experiment they used a few different energies of electrons in doing this. So that's what we're going to do first. We're going to send off some pulses of electrons. So that's our first thing, and we've got the measurement we're going to take. We're going to use an oscilloscope to measure the time. So what we also need to measure is the distance between the accelerator and the plate, because if we have distance and time, we can calculate velocity. So let's get that one down. Okay, so what we've got now, so in terms of the criteria for the question, we've now got our diagram and we've got our explanation of how we would measure the velocity. Now we need to explain how the kinetic energy was determined. So that's done by calorimetry, or essentially measuring the change in temperature of the plate. So let's do that next. Okay, so we've got the amount of energy now transferred to the plate. So if we know the energy transfer, we know the number of the electrons that have hit the plate, we can essentially work out the energy that each electron has from that. So let's do that now. So that's how we can actually determine the kinetic energy. And so what was done is they did this for a range of different electron energies from the particle accelerator, and they compared that with the prediction from relativity. So that's what this was all testing. And so that's what we've got written here, the final stage, what we were trying to achieve from this experiment, testing the predictions of relativity there. And we haven't just done it for one electron energy, we've done it for a range of possible energies to check it's valid for all of those different ones. Okay, so that's part 1. Let's move on to part 2. So a scientist conducts an experiment similar to Bertozzi's experiment and reports that when the electron speed is 2.93 times 10 to the 8 meters per second, the kinetic energy is 2.4 mega electron volts. Determine whether these data are consistent with the result expected using the theory of special relativity. So let's do the predicted value first of all. We want the kinetic energy that's predicted. Okay, so for the terms, we're going to need the first part of your kinetic energy, and then over the square root of 1 minus v squared over c squared, and then subtract this. Okay, so this would give you your predicted value. So let's calculate that now. So let's factor out the m0c squared first of all to make this more straightforward. Like this. And then what we can do is put in our values. So we've got the rest mass of an electron, times by 3 times 10 to the 8 all squared, and that's multiplied by square root of 1 minus 2.93 over 3 all squared minus 1. Those are our values, and when we put that in, that comes out as 2.99 yada 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 times 10 to the minus 13 joules. And let's convert that into mega electron volts, seeing as that's what we're dealing with. So divide by 1.6 times 10 to the power of minus 13. It's 1.87 blah 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 mega electron volts. That's the energy predicted from relativity. We've got a value of 2.4. So let's find the percentage difference of our value from that 2.4 and to see how good the agreement is. 2.4 minus 1.87 divided by 2.4 times by 100%. This is our way of comparing an estimated and a real one. So 2.4 minus our answer divided by 2.4 times by 100 gives you a 21% difference there, which is pretty damn high. And so you would not see this experimental value as any sort of confirmation of this prediction, because that's incredibly high. So let's have that final note. Okay, so I've just had a look at the mark scheme for this question, and for some reason they've got a different value here calculated, but I've done my maths a few times over and I keep getting the same answer, and I checked with an online calculator and it gets the same answer I do, so I think there's something wrong with the mark scheme for this question, but let's press on anyway on to question 4. So we're going to look at a transmission electron microscope where we're accelerating electrons using a potential difference, and we want the wavelength to obviously match up with whatever our sample is, so we're going to have a potential difference equivalent to that. So identify which of the following represents a relationship between lambda and V. So we know that the change in electric potential energy is going to be equal to the kinetic energy of the electron. So we've got this relationship here, and we also know that the velocity is given by h over m lambda here. So let's make that substitution. So EV is going to be half m times by h over m lambda all squared. So from this we can see that V is going to be directly brought into 1 over lambda squared, or lambda is going to be directly brought into 1 over the square root of V, which is answer D. So that one. Okay, so the TM operates using wavelengths about 0.1 nanometers. Explain why operations at such wavelengths makes the instrument such an important research tool. Well, this is the sort of size of an atom. 0.1 nanometers is also known as an angstrom. So we're going to get this electron being diffracted by atoms because they're about the same size as this wavelength. So that's really good. And the other thing is that at small wavelengths we get a very high resolution as well. So those are essentially two benefits to having such short wavelengths for it. Okay, so those are two things you should know. So you should know the resolving power essentially is determined by the potential difference and the wavelength. So the bigger your potential difference, the smaller the wavelength, so the higher the resolving power, the higher resolution images you get. Let's move on to part 3. So the last question, state and explain 2 factors which limit the detail of the image produced by transmission electron microscopes. So the first problem you get is that not all your electrons are necessarily at the same energy and therefore not necessarily at the same wavelength, so you get some blurring of your image due to that. So that's the first one. Let's get that down. Okay, so that's the first source of errors in your electron microscope. And the second is that when electrons actually encounter your sample, they are going to be slowed down, which changes their velocity and changes their wavelength, giving you different diffraction for each electron wave. Okay, so that's the second source of errors in your microscope, and those are going to lead to blurring of your images for that point. So that's what we're going to get. Okay, so that completes this paper. If there's anything that you'd like to ask about, please do feel free to comment and I'll try and answer your questions as best I can. Well, I hope you found that useful to review your working through this paper for turning points.